Hello, everyone. This is a very curious sort of a situation in the entire country, especially in Bengal. I'm recording this after the hurricane Amphan struck Bengal and Odisha and Bangladesh, I think, as well. And thousands of people are homeless, shelterless. It's a very weird kind of world where uh, poor people, destitutes, are struck twice, once by a disease and then by a hurricane. It seems like there is no end to this misery. It's happening over and over and over again, and I don't know what to do because this is a very weird situation. So I thought the only thing that I can probably do a little bit is mathematics, and I'll just talk about a little bit of mathematics, and some of my anxiety would be relieved. And this is not a general video. I mean, I'll just talk about mathematics and try to tell you what I have learned a little bit about mathematics. And maybe you can tell me something about your feedback, um, just to keep our minds off from all the bad things that are happening around us. Recently, I learned about something very interesting. It's known as a convergence action. Convergence action. This is the book that I'm referring to. It is by one of the most powerful mathematicians existing. It's called Bryant Bowditch. There is a The name of the book is Tree-like Structures Arising in the Continua and Convergence Groups. It's a very short book, as you can see. It's like a memoir. And the beauty of this book is that much of it you can understand without knowing any fancy mathematical ideas. You need a little bit of topology or a little bit of group theory, but only a little bit at least to get started off with. And Bowditch is actually a very, very thorough kind of a mathematician. So he puts all the definitions in place, he puts all the ideas in order so you can really understand what's going on. And that's really, I like that very much. Uh, One of the things as students of mathematics we want to do is we want to understand what's going on, right? Uh, so I'll talk a little bit about convergence action because I found it really interesting. So imagine that there is a space like maybe a string like this, and on that space there are some attracting and repelling forces. So maybe I can say it like this, that there is a space where there are some forces acting on the space. So maybe the space is like this, a string, the one that I drew here, a string, and the forces are acting on this particular red string. So they are moving points on this red string. They are moving points on this red string. And these points, you can think of these points, in my mind at least, they're like beads. They're like beads, little pearls, you can think of it like that. And the forces are pushing these points all across this wavy string structure. This is my space M. And these forces would take these beads from one place to another. And we are really trying to understand how these forces act on the beads. And in very special cases, these forces act as a convergence group on these beads. What is a convergence group? Well, in a convergence group, it's a very, when I say group, you can think about collection of all possible forces. So maybe I can write that. So when I say a group, it's sort of a collection of all possible forces. So you collect all the forces that you can think of and you make them act on the space M, and you want to see what happens as an output. Where do the points go? You really want to understand the movement of the points. In a technical word, you can say you want to understand the dynamics. You want to understand the dynamics of what's happening. So it's just a technical word. What it really means is you want to know when the points are moving, how they're moving. That's the real thing. Okay. So in the case of convergence action, so this is a very special case I'm talking about. It's a convergence group. Convergence group. So it's not all possible group, but it's a very special type of set of forces. In that, something very nice happens. There is an attractor point. So if you take any sequence of group elements, I'll write that. Take any sequence of group elements, G1, G2, G3, and so on. So you should think of each of them as forces. These are types of forces. When I say forces, maybe the first one is pulling, maybe the second one is pushing, maybe the third one is reflecting, and so on. I should really say that they are homeomorphisms of M. So technically speaking, they are homeomorphisms of M. But that's a very technical term. I don't want to go there. I just want you to imagine what's going on. Okay. So this G1, G2, G3, G4, G5, all of these things, they are different types of forces, and you picked up a sequence of forces. You picked up a sequence of forces, G1, G2, G3, Gn. There are infinitely many of them. You picked up one sequence. This is the definition of convergence action. I'm giving you the definition of it. So when you pick up any odd sequence, if you pick up any sequence of G1, G2, G3 forces, you will get a subsequence. And subsequence means maybe you get the second one. I'll write that. Maybe you get the second one. Then you get the 31st one. Then you get the 253rd one. So you get a subsequence of forces which behaves in a very interesting way. And what is the interesting way? That for that, you will get an attracting point and a repelling point. An attracting point and a repelling point. So maybe the attracting point is alpha. Attracting point, let's call it alpha. So suppose it's alpha, and repelling point is beta. The attracting point is alpha and the repelling point is beta. Okay, so let's see what's going on here. It means that what's happening is that if you take any x, so this is M, this is your alpha, suppose, and this is your beta. This is your alpha and this is your beta. If you take any x in M and if you push it by these GIs, G1, maybe G2, G31, G253, you are pushing x, you are hitting x with these, then this x will move toward alpha. So alpha will act as a suck-in point. alpha will act as a suck-in point for all x except beta, for all x except beta. So for all x in m minus beta, gki of x will go to alpha. So the suck-in point will take in all of them. And for all x in m minus alpha, gki inverse x goes to beta. So in other sense, if you hit it by the inverse of the forces, so if you were pushing in the left, you should think about the inverse as pushing to the right. Okay. So if you do that, then this gki inverse of x goes towards beta. So this is the repelling point, and this is the attractor point. So attractor and repeller. So the point is this, that for any collection of forces, this will be true. For any collection of forces, this will be true. If you take any sequence G1, G2, G3, G4, G5, and so on, you take a subsequence, you will get a subsequence and 2 points alpha and beta for which this will always happen. It happens so that if you take a group, Shomali, this is a very different topic. You can apply to our website actually. Okay, it's a different topic, but surely you can apply to our website. You can take the classes and learn some good mathematics for RMO and INMO. We have the courses going on there as well. So sure. Okay, all right. So now the way convergence groups appear is they appear as convergence actions. This kind of actions appear when you look at a group and you look at its action on the boundary of the group. It's possible to define a space called the boundary of a group. When you define the space called boundary of a group, in a way, this is done like this. So if you take a space, let's say now I'm taking the entire oval. Then in a way, if you choose a point x0 inside the space and you look at all the roads going outside this toward infinity, all the geodesic paths in some sense, if you look at all the geodesic paths emanating from x0, so x0 is a point in the space, x0 is any point in the space, and you are looking at all the geodesic paths going out of this point, then the collection of those paths will create something called the boundary of the space. So you take a space X and you choose a point x0, choose x0 in X, and you look at all paths going out of x0, So these are geodesic paths. Geodesic means they are sort of straight lines. Of course, how the straight lines will look, that depends on the metric or the distance function that you are using. So that's a very different topic actually, but how straight lines look depends on how you define a distance function. So if you think a little bit more about that, you will probably reach the realm of hyperbolic geometry. Anyway, so you take a point x0, you take all the geodesic paths coming out of it. So you collect collect all such paths, and you can analyze this set of paths to create something called the boundary of the space. It's written like this: the boundary of the space. So in some sense, I think this is a beautiful interpretation in a way, the way it comes to my mind at least. The boundary of a space is basically all roads leading to infinity. So even if you have an infinite universe, and if you want to imagine its boundary, one way to do it is you take any point in the universe and look at all the geodesic paths going out of that point toward infinity. The collection of all those paths is the boundary of your universe. And one can show that this is a well-defined topological space. This collection of paths is a well-defined topological space. And in the case of some groups and some spaces, the way the group acts on the boundary is a convergence action, the one that we just talked about. So anyway, the key takeout of this particular Adda, I would say, would be that if you want to analyze a group, first look at how the group is acting on some space. In fact, you would want a space, you would want to construct a space on which the group can act on. So if you imagine the group elements as forces, then you should try to construct a space on which these forces can act on. And then you look at the boundary of the space, and you think, okay, how the group is acting on the boundary. If the boundary is well defined, of course, you have to check that as well. But now you know what is a boundary. A boundary is a collection of all the paths coming out of a single point in the space. So it's just a collection of roads. It's possible to imagine the roads as points, and then use that collection of points and think of the group acting on that collection of points. And there you go. You have, in very special cases where the group, there are some technical terms, for example, for hyperbolic groups. So I don't know, I've not defined what that is, but there are some special type of groups called hyperbolic groups, and some special type of spaces called delta hyperbolic spaces. Very simple objects, but I have not defined them yet, so I'm not using them. But these are examples where the group acts on the boundary as a convergence group. And then you see beautiful dynamical properties of the boundary, of the action, because then you sort of see the points moving in the boundary, and you see everything coming into life in a way. Okay. All right. So again, you can look into Bodich's book. It's a very nice book. It's tree-like structures arising from continua and convergence groups. And you can learn more of these beautiful ideas. I will see you whenever I see you next with some new problems. Till then, stay safe and try to help others if you can in these very testing times. Bye, all of you. Take care.